Okay, so we have so far learned how to calculate both definite and indefinite integrals, and specifically, most recently, definite integrals. We saw how that they would give us a number. Um, so, as has been teased several times now, that's what we're going to use to find areas under curves or under graphs. So that's what we're going to look at in this session. How does that work? Or effectively, how do we use it? And can we answer some questions related to it? So this is when it gets really interesting. Just to demonstrate what it is we're actually going to be doing, or what tool we're about to get, have a look at this graph here that I've plotted. So it's 1/10 x squared is the red graph, and then it's additionally bounded by these two vertical lines, the green and the purple one, at x equals 2 and x equals 3. Just firstly, have an estimate. What is the area under that graph in that yellow region? Do make sure you take into account the units of the graph. So, for instance, 1 square is not necessarily an area of 1. So take that into account. See what number you get, and then in a moment we're going to see if we can confirm how accurate your guess might be. So pause the video and just make an estimate of what you think the area is. Okay, so let's see, or let me show you how you would actually answer this question, not by estimating, but by using integration. So I'm just going to demo how I would do this and see if you can start to see what the method might be in general. So I'm going to do an integral of the function that we were interested in, the one we took the area underneath. And for my limits, those two numbers on the top and bottom, I'm going to choose those two vertical lines, the number at which they crossed the x-axis. So the first one, which will be my bottom, was at 2, and the second one, which will be my top, was 3. Now let's work out what this is. So I do the integration, put in my limits here, and that's going to give me 1 over 30 times 27, 3 cubed, minus 1 over 30 times 8, which is 2 cubed. So all in all, I've got 27 minus 8 all over 30, so that's 19 over 30. And that's it. That's the actual exact precise answer for the area under that curve. And this is generally the way we're going to be doing it. You're going to be performing the integration of the curve that you're interested in, and then for the limits, to make it a definite integral, you're going to place these two imaginary vertical lines that define the boundary of where you start and where you're ending the integration. And of course on the bottom, as we saw in the example, it's going to be bounded by the x-axis. So you've kind of got these four walls. The top wall is the graph, the left and right are these imaginary vertical lines defined by the limits, and the bottom wall is the x-axis. So I'm just going to define this this rule now a bit more specifically so we can see how it works in general. So this is the general case of the kinds of problem that you can now solve using the tool of definite integration. If you have some function plotted, let's just draw a sort of squiggly line representing our function, call it f of x, and you want to calculate the area under the graph, so it's always under the graph for this positive valued function, you define two positions on the x-axis. There'll be two numbers. In this case, I'll call them A and B. In the previous example, they were 2 and 3. And you've got these two then imaginary vertical lines. And you've also got the black line horizontally, the x-axis. I can now calculate this area, and so can you. And to calculate it, you just have to do the integral of whatever that function is, the red line, and just choose as your limits. The bottom one is the one on the left, the limit on the left, and the top limit is the number on the right here. Okay, so here, what I'm calling the bottom limit is also, you could think of it as the left limit, and what I'm calling the top limit, you can think of also as the right limit. Okay, so the number going on the top is the same as the number that was on the right on the x-axis, and similar rule for the a limit there. Okay, so that's our general method, and that was what the whole point of learning about integration was. We learned about indefinite integrals first, just so you know how to do the method. Then you learned about definite integrals, so you knew how to put the limits into the expression that you get. And now you should understand why we did all that in the first place, because now we can answer questions like this, which previously you couldn't. You would have just had to guess or create an estimate. So let's look at an example of the kind of question you can now solve, and see if we can complete it together. So you've been asked to find the area of the finite region, as opposed to infinite, between the curve with equation y equals 20 minus x squared and the x-axis. So since we don't have a diagram, I think it might help to graph this first. So we're going to want to create our axes and then graph this function. Now, in order to graph that, that's going to use that skill of finding the critical values where it crosses the x-axis, and then just noting the general shape of this quadratic. So we're probably going to want to factorize this quadratic. So I'm just going to rewrite it in the more standard order. Then let's have a think about how this might factorize. So I'm going to write this as follows, with a minus on the outside, so that we don't have to worry about the minus x squared. And then it should be 5 and minus 4, shouldn't it? X plus 5 and x minus 4. Yeah, that works. And then remember, I've still got the minus here on the outside. You could put that inside, perhaps turn this into 4 minus x, but I'm going to leave it on the outside, so that's fine. The critical values then, or the crossing the x-axis, is when x equals 4 and x equals minus 5. So let's mark that on. That's 4 there, let's say. That's minus 5. And then what is the general shape? Well, because the coefficient of the x squared is negative, we remember it's the n shape rather than the u shape. We should also get the y intercept actually. So when x is 0, y is 20. Let's mark that on. Okay, and now I've got my shape. So it looks something like this. Okay. Right, and then what was the actual question? Find the area between the curve with that equation and the x-axis. So remember, the x-axis, horizontal black line. So I think it's well defined, isn't it? They're saying find this area here. Okay. Okay, that's the area that they want. So according to what I just said about the method, what we're going to need to do is integrate that function. We also need to choose the limits though. So in this case, the limits might not be completely obvious. Have a think while I just write the integral. So in this case, our imaginary vertical lines, or the limits, they are the critical values themselves, right? They are here. Reason being is if they were, for instance, closer together, let's say, for example, my left limit was here, then I wouldn't be including this area. I would be chopping off a bit. Likewise, if I had put the limit further to the left over here, then you're going to start including this area. So because I don't want to include either of those or do any chopping off, the limits need to be where they are, at -5 and 4. And then the left limit -5 becomes the bottom here, and the right limit of 4 becomes the top limit here. And we just calculate this definite integral, and this should give us the answer for the area. So let's work it out. So we'll get 20x minus a half x squared minus a third x cubed from -5 to 4. I'm going to have to do some substitution. So the first one I put in 4 and I get 20 times 4 is 80, minus a half 4 squared, that's -8, minus a third 4 cubed, that was a bit trickier, -64/3, and then let's put in the -5, we get -100, -25/2, and -125 times a minus, you get this. Okay, at this point you can probably just use your calculator. And it turns out the answer is this. Okay, so 121.5 is the exact precise area between that curve that you can see and the x-axis. Okay. Right, so before we look at a couple more examples, I just need to talk about something which we hinted at a moment ago, which is this idea of the negative areas. Now, this doesn't mean you're actually going to talk about areas as being negative. Areas are always positive values. You can't say, you know, a room has -10 meters squared area. But this is more about noting an important way in which definite integrals work, in that sometimes they'll give you the correct area and sometimes they'll just give you the negative of the correct answer, and you need to know in which scenario that will be. So the way it works is as follows. Let's look at a sort of fake function, and I'll make it quite a complicated looking one, so we don't need to actually describe it, but let's say I have a function that looks something like this. Okay, that's my function. Now, when we talk about finding the area between two limits, let's say I pick a limit here and I pick a limit here. Then the area is going to be this bit. Okay, so that so far should make sense. If I pick an area, for example, here, with these two limits, then the area that the integral is going to calculate is going to be this, but it's going to give me a negative answer. So what I mean specifically is, let's say this is f of x, and let's not be too general. Let me put on some values. Let's say this is the value, let's say this is 2 and this is 4. Let's say over here I'm at 11 and 12. Okay, so I've just made those numbers up. Don't worry about why I've chosen those. But here, that area is exactly equal to the integral of f of x between 2 and 4. Whereas this area over here, if you were to integrate 11 to 12 of this function, you'd actually end up with a negative answer, which doesn't make sense because areas are of course positive. So what you have to do is just take the negative of your answer and you'll have the correct answer. So the reason it flips is simply to do, and this is intuitive, isn't it, with the fact that it's below the x-axis rather than above it. So if you're finding an area between the x-axis and the positive values of the function, you just do what we did before. If it's between the x-axis and negative values, so it's below the x-axis, do what we did before, but just stick a minus at the front, and then the final answer will end up being positive. The integral itself, though, will be negative. So then the final thing we need to think about is, what if I do something awkward like this? What if I pick these two limits? Okay, and I want to know the total of that area and that area. Okay, what I can't do is do it with a single integral, because this part is going to be giving me a positive value and this part will be giving me a negative value, and it will cancel out to some extent, which means it won't give me the correct answer. I want to know that area plus this one. I don't want to take them away from each other. So if you were asked to find an area like that, the solution is to split it up into regions where it's either fully below or fully under the x-axis. So for instance, let's make some numbers up here. Let's say that's 6, that's 7, and that's 9 on the x-axis. Then what I would do is find the integral from 6 to 7 of the function. That's going to give me this area, and then I would add to that the negative of taking the integral from 7 to 9, like this. So I work out the two numbers separately and then add them together, and that will give me the total area. And of course you'd have to figure out, that this crossing point here probably is 7 in this case. It may not be given to you. Okay, so don't worry about the specific numbers. The key thing is the concept. If you integrate the function while it's below the x-axis, you'll be getting negative numbers. So you need to flip them to make them positive, and then it will be the correct answer. If it's above the x-axis, don't worry about it. Do as we did before. If it's a mixture, then you need to do several integrals and choose limits by splitting up the function into sections where it's only above or only below the x-axis. Okay, so let's look at an example of this. So we've been given another quadratic. In this case, it's already been factorized for us. So the key values are crossing the x-axis at 0 and 3, and the y-axis is going to be crossed at -3. That's when x equals, oh no, sorry, what am I talking about? It'll just be at 0. Okay, and then it's a U shape because effectively this is x squared minus 3x. This part is positive, so it's a U shape. Let's draw that in. Okay, and we want the area of the finite region bounded by the curve and the x-axis, that's this part. Okay, so this is one of those cases where the area we want to find is fully below the x-axis. Our imaginary limits, I mean they're not really imaginary, our imaginary lines representing the limits are here. So what we need to do is find the integral from 0 to 3 of the function, which in this case is x squared minus 3x. But then, because it's below the x-axis, we're going to take the negative of that, and it will give us a positive answer at the end. What you may want to do is not worry about the negative, get your negative answer, and then just change it at the end. It shouldn't be possible to forget to do that because, as we said, an area is always positive. The key thing is that you just don't forget about the negative. Let's try it. So I integrate. Keep my limits there. And let's substitute in. So I'm going to put in 3, I get a third 3 cubed, that's the same as 3 squared, minus 9 times 3 over 2. And then take away from that, subbing in 0, we just have 0. Okay, so the final answer there, 9 minus 27 over 2, so that's 18 minus 27 all over 2, so that's minus 9 over 2. Okay, so as you can see, the integral has actually given us a negative answer, which doesn't make sense for an area, but we know why it's negative. It's because we were below the x-axis. We flip it, and the final answer is 9 over 2. Okay, cool. So let's look at one more example, and I think this one will then mix the positive and negative areas, and we'll see how that's done. So we've got our equation conveniently factorized, so we can see the key values. They are at 0, at 1, and at minus 3. So let's put that here, minus 3. It's a cubic, and we're going to have to integrate it, so we're going to have to multiply it out. So let's just do that first. That's x squared minus x times x plus 3, which gives me x cubed plus 3x squared minus x squared minus 3x. So that's x cubed plus 2x squared minus 3x. Okay, that's our function. So since the coefficient of the x cubed is positive, we know it's this kind of shape. So let's put that in. So it's going to be something that looks a bit like this. Our cubic. And we're going to find the finite area between the curve and the x-axis. So we want the total of that plus this. So this one is the integral from, and then we look at the limits, it's minus 3 to 0 of the function. And this area is going to be the negative of the integral between the limits 0 and 1 of the function. There. And then we're going to add those two numbers together. So since we're going to be integrating the same function effectively twice, it makes sense to find the indefinite integral and then we can then use that to put limits in both cases. So let's find the indefinite integral. If I just integrate y with respect to x, what do I get? I get this. And I suppose a plus c, but we're not going to have to worry about the plus c when we put the limits in. Okay, and then let's put limits in. Let's do the first one. So minus 3, 0. What are we going to get? When I put in the bottom one first, minus 3, remember we're effectively substituting into here. And don't worry about the plus c because it's now a definite integration. It gets a little bit complicated at this point actually. I would suggest we use our calculator. So put minus 3 into that function and let's see what we get. So I get, in that case, minus 11.25, putting in the minus 3, putting in the 0, which is on the left there, we just get 0. So in this case, it's 11.25. And then from 0 to 1, let's put in our two limits. So it's top limit minus bottom limit. In this case, the 1, well, that's just going to be a quarter plus 2/3 minus 3/2. So that turns out to be minus 7/12. And you put in the 0, we have 0 here again. So we have here minus 7/12. And in fact, let's change this one to minus 45/4. Not minus, sorry, plus 45/4. So the first one, we've got the answer is here. And this one, because it's below the x-axis, we take the negative of what the definite integral gave us. It gave us minus 7/12, so this is actually an area of 7/12. And then we're basically done. We just need to add those two together. So our final answer, let's note it here, is the sum of those two areas. And in this case, we get 71/6. And that's it, done. Okay, so hopefully that makes sense and that covers effectively the main principles at work here. So you've learned how to apply definite integrals to solve area questions, and you've also hopefully understood how to deal with the scenario where the function is below the x-axis. Okay, so let's try some questions. So I've got 3 questions to try in total, 2 on this slide and 1 on the next slide. So hopefully not too many, enough to make sure you've understood the concept. Have a go at these 2, and when you've done those, there's one more waiting for you. You can pause the video now. Okay, and finally, have a look at this one here.